Good morning, everybody. Welcome to episode 7 of AlgorithmsThread. Today I'm going to be talking about a really cool algorithm that lets you look at all pairs of points and keep all of the other points sorted in some interesting order while you do that. So it's a really cool algorithm. As far as I know, it doesn't have a name, so I'm going to call it all point pairs. And I'll show you how it works just kind of by example. So the first problem that I'd like to talk about is this is a Southeast Regionals problem. I think it's called like triangles or something, but I'll have a link to it in the description or in the Codeforces blog post, so you can check that out. And basically, in this problem, you're given some set of points. They're not necessarily like ordered in any way, but you do have the nice restriction that there are no 3 collinear points. So you don't have any 3 points in a line. And I think how I've drawn it now, that looks to be the case. We'll assume that this line here goes above this point. But yeah, so that seems to be fine. Now once you have these points, you have to find 2 things. You have to find the biggest rectangle, or biggest triangle by area, and also the smallest triangle. So let's look at this as 2 separate problems for now. If we're looking for just the biggest triangle, one thing we can keep in mind is, say we've got some of these points. Let's say we think for some reason this is the biggest triangle. It turns out we can show that this triangle isn't the biggest triangle, and here's why. Let's say we have the convex hull of all of these points. Oh, and there you go, convex hull. This is why we did the last episode, right? It all comes full circle. So if we have this convex hull, what we know is if we fix some base of the triangle, maybe this is the base that we've fixed, the area of the triangle is only determined by how far the other point is in this direction or in this direction. It doesn't matter how far left and right it is, right? Because the area of a triangle is base times height over 2. So all we want to do is we want to find the farthest point in this direction. And we know that if you have some line and you sweep the line down, right? If you sweep a line like this, keep moving it down, the first point it hits is going to be on the convex hull. So what we can do is we could increase the area of this triangle from what it was there to this right here by replacing one of the points with some other point on the convex hull. Now we did that for this bottom edge, but we could also do that we can make that same argument for any other edge. So let's say we want to do that argument for this edge here. We can replace this point with some point on the convex hull. So maybe instead of that point, we use this point here. And when we do that, we've just found a strictly better triangle. Now we can do that a third time. We can do that argument for this top edge here, and that will let us replace this bottom point with some other point that's on the convex hull. So now we've just made our point better, and we've made our point better until we have 3 points on the convex hull, or a triangle better rather. So now we know we have 3 points on the convex hull. We don't necessarily know, like I haven't proven that these 3 points are going to be the best decision, but I have proven that these 3 points are better than the triangle we started with. And that was some triangle that wasn't 3 points on the convex hull. So once we know that our answer is on the convex hull, what we could do is we could just get the convex hull in n log n like we talked about in the last episode. And once we have that, we can brute force one of the points. So let's say we know this point here. If we brute force what the second point is, now we have this line here. We just want to find the farthest point in this direction and the farthest point in this direction. We talked about how to do that in log time, so we could do this in n squared times log n. And I assume that the n cubed is pretty obvious, so I won't talk about that. Basically, you can just brute force all triangles. That was the first way of doing it. Here's the second way, in this n squared log n. And I'm sure many of you already have this going through your head that this binary search is a bit wasteful, because it should be pretty clear that if the second point here, as this second point moves over, the third point is also going to move over. That should just feel right. I'm not going to go through super clever details of that, but basically what we can do is we can do a 2-pointer sweep. If we fix this point, as we move this point in a clockwise or counterclockwise direction, this point will also move in a counterclockwise direction. So we can do a for loop for this point, and then just a while loop for this point, and keep moving it over as long as it gets better. So maybe this is the optimal triangle for these 2 points being fixed. And now we want to move this point over 1. So we move this point to here. Now we can see we just need to check these two, and then this is better. And eventually it'll start getting worse. So if we were to move it there, that would be a worse triangle. So now we have this optimal triangle here. So now we found all optimal candidate triangles that include this top point here as the point that we're fixing. So we'll try that for all starting points. Eventually we'll find the best answer. All right, so that's how we find the biggest triangle. That should be pretty simple, and that doesn't require this new method that we talked about. It's just a really interesting use case of convex hull, and that will run in just n squared. So we saw this problem in a contest. I saw this problem actually after I saw the smallest triangle version of it as well, and I thought n squared log n was the best you could do because I hadn't been introduced to this, but it's not. You can do n squared, so we've just talked about how you can do the n squared. But you can also do, if you want to solve both of these problems, you can do it in a way that's just pretty much the same difficulty as just solving the smallest triangle one. So now let's talk about the smallest triangle case. This should be a bit more interesting, I guess. And when I say interesting, maybe I just mean harder. Because there's no reason to think that the best answer is going to be on the convex hull. Really, like, there could be some really small triangle in here, or there could be some triangle with like very small area that's like this, right? So that might be really close to a line, might be really skinny. That might be the best answer. We don't really have any bound anymore on what this optimal triangle is going to be. So what do we do? Well, let's pause for a moment and stop trying to come up with a solution. Just think about what we're asking. So if for some reason we knew one edge of this triangle, and it turns out later on we're going to brute force this edge, what we want is, if you go straight up, what is the first point after these points that you would find? And in this case it would be this. So this point here, since it's the first one going like perpendicular to the edge, this would give us the smallest triangle if you have to use this edge. And we could do the same thing in the other direction. So in the other direction, it looks to me like it would be this one here. That would be the smallest triangle, smallest area triangle. Cool, so that's what we're looking for. But the concern is, how do we find that in some quick way? Like, really, it would seem like the only way to do that would be to look through all other points. And if we're only checking one edge, that is the only way of doing it. We would have to do order and sweep, we'd have to check every other point. But we can keep in mind that, like, we can take more advantage, like we can abuse the property that we're going to check all pairs of points. We're not just going to check this pair. What we can actually do is we can keep all of the points sorted by some, like in some direction. So the way I usually like to do it is initially the points will be sorted like in this direction here. So pretty much going straight to the right and then tie break by going down to the left. So initially we'd have 1, 2, 3, 4, so to the right. So it looks like this is farther right, 5, 6, 7, 8. And now what we're going to do is we're going to very slowly take this vector here that we're sorting it by, and we're going to rotate it very slightly. And we're going to keep rotating it, and eventually we'll rotate it all the way till it's 180 degrees from where it started. And when we do that, what will happen is when the vector is pointed in this direction, when the points are sorted like this, what will happen is these 2 points will be right next to each other in the array. So when it's sorted like this, we'll have, I guess I'll redo the numbers. We'll have 1, 2, or I guess it'd have to be 1, 2, 3, 4, 5, 6, 7, 8. So if the points are sorted like this, we know these two are going to be right next to each other because it's, I mean, their line is it's perpendicular to the direction it's sorted. So they'd have pretty much equal value. And in addition to them being sorted, or them being right next to each other, if we look right, what comes right before them in the sorted array, that would be this 3 point. That 3 would be the smallest triangle that you could make if you used both of these points. And the thing that comes right after them will also be right next to them. It'll be the 6. So you've got these 2 points next to each other, and you want to consider the 2 triangles relevant to this point you can use the 6 and you can use the 3, the thing that comes right before and right after them. They're not necessarily in the middle, obviously, they could be anywhere. But what we can do here is we can, like, if we are smart about when we check each edge, if we know where each point is in the array, when we check an edge, we know where to look in the array in order to find our optimal candidates. Cool. So that will give us, it'll give us those. But we still have this question. We're trying to keep this array sorted as we rotate this vector. How do we know how to do that? That seems like a very difficult thing to do. We might have to just sort the array a bunch of times, and that would be, well, like, it would change roughly n squared times, and we would have to sort it each time, so that would be n cubed times log n, which obviously would not be fast enough, because n is quite big. Maybe n is like 2000 or something. So we don't want an n cubed, we want like an n squared or something. All right, so how do we do that? Well, I'm going to make fewer points because I think that might be easier to keep track of. So maybe we'll just have these 3 points here. Let's draw it like this actually. Here we go. So we've got this A, this B, and this C. And initially things will be sorted like this. So initially our array will be A, C, B. But eventually, what will happen is this arrow will be pointing like in this direction here. When it's like this, then our array will look like A, B, C. And now the question is, these two just swapped places in the array. When did that happen? Well, let's look at the vector between them. That'll look like this. Or I guess let's do this vector here. They'll swap places when the vector that we're sorting by is equal to this. So we know that's one swap that will happen in the array. We can also look at this swap here. And A and B will switch places when that vector looks like this. And finally, we can look at A to C. And A and C will switch places when it looks like this. So we also know the following thing. When B and C switch places, that means right before they switch places, that is the perfect time to process this edge right here. Because we know they're right next to each other, and we're sorted by stuff perpendicular to that. So that's when we can process that pair of points. Okay, so now we have these 3 instances in which 2 points will switch positions. We can take these 3 instances and we can sort them radially. So we can sort them like this will be the first one, this will be the second one, and this will be the third one. And we can also keep track of which 2 points get swapped in the array. So in this case, we want to swap B and C. In this case, we want to swap, this is A and B. And I guess in this case, then it would have to be A and C. And we can have this like list of events. We can process it in this order, and we can keep track of everything as we go. So awesome. That is pretty much the TLDR of this method. And that solves the smallest triangle case. Just really quickly, I'm going to go over how you can use the same method to solve the biggest triangle case, because I think it's quite nice. So we know the answer is going to be somewhere on the convex hull. And maybe, let's say, for some reason, well, we know all 3 edges are going to be in the convex hull, really. But the important part is, when we hit this edge here, if we can find the thing farthest in this direction, that's either going to be the first thing or the last thing in the array. So for the smallest triangle, we can just check the thing above and below it. For the biggest triangle, we can just check the first and last thing in the array, and after we do that, we will have our answer. Fantastic. All right, so that is the first problem. The next problem I'd like to talk about is a code forces problem. I wasn't able to find this before. I'll look a little bit more, but yeah, I might not be able to link to this, unfortunately. But here's the problem. I just remember it. The idea is you're given a bunch of points, again, and maybe like n less than or equal to 2000, again, familiar theme here. And the idea is, what you want to count is how many ways are there to take these points and then split them up into, or like to pick 6 points that make 2 triangles. Not really even how many ways to pick the 2 points. How many like pairs of triangles are there that look something like this. So that would be one way. Another way that would be valid would be like this for these points. Also, you're given the constraint that you have no 3 collinear points. So that would be another valid way. Some way that would be invalid would be a case in which the triangles intersect. So if you have something like this, that would be invalid. That wouldn't count. So now the question is, how many ways are there of doing this? And I'm pretty sure you have to print it under mod. Although you might not have to, depending on how big n is. But that doesn't make the problem any more difficult. So now, yeah, how do we do this? We again have, we've got this nice technique we've just learned, and it's in this video, so chances are it's going to use that nice technique. There's your metagaming right there. But here's the interesting observation we can make. If we have 2 triangles, it doesn't really matter what they look like. As long as they don't intersect, there's this math theorem, I forget what it is, but the theorem is that as long as you have no 3 collinear points and they don't intersect, there will be exactly 2 interior tangent lines. So here are the 2 interior tangents, and basically like it's going to touch this one here and touch this one here, and then touch this here and touch this here. Here's the proof for why there are 2. If you draw some line between them, you can take this line, now you can rotate it in one direction, and eventually you'll hit the first one, and then you can rotate it till it's the other one as well. You could also rotate it in the other direction. There has to be some separating axis theorem is what it's called. There has to be some separating axis right here that will split them in half. Otherwise, they're not separated. Okay, cool. So here are these 2 lines. What we can do is we can only look at, let's only look at this line here. So we'll only look at one of them. But now what we can do is if we have this line, or let's define this pair by this first line. And maybe we'll double count everything. And if we double count everything, we just divide by 2 at the end, so that's no big deal. But if we define it by that line, then let's draw that line in this picture here. So maybe we have this line here. We know this first triangle, it's got to include this point. It also has to be entirely, like the other 2 points, both have to be on this side. And the second triangle has to include this point, and the other 2 points have to be on this side. So really all we need to do is if we have this line, we can count how many pairs of triangles is this line the relevant separator for by just doing, let's see how many points are on this side of the line, how many points are on this side. For each, we'll do n choose 2, because we have to pick 2 as the other half of the triangle. So maybe we pick these 2 here, and maybe we pick these 2 here. And once we know how many ways they're doing it on one side, how many ways on the other, those are independent, obviously, because they're separated by the line. So then we can just multiply them together, and now we can count how many ways does this line separate 2 groups of triangles. So what we need to do is basically we need to see how many things are on each side of the line. And that should be very easy to do, because if we have them sorted perpendicular to this line, then we just want to see, all right, how many things are above this in our array? How many things are below this in our array? And if we store what index everything is in the array and we maintain that, it takes a little bit of maintenance, but it's fine. Then we can just do some quick math, easy math, to figure out what that number is going to be. Okay, cool. So that is problem number 2. There's one more problem that I'd like to talk about, and that is, it's a good problem. It's from a contest that is a bit silly. It's from CodeJam for Women. I personally don't think women are like a second-class citizens who need their own contest in order to be able to feel safe programming. I feel like they're just as good as men at this, so they can compete against me and against tourists and everybody else if they'd like to. You don't need to make a special category for them as if they're disabled or young children or something, but whatever. So not a fan of the contest, but I am a fan of the problem. The problem was kind of interesting, and the problem is you have a bunch of points again. Again, you have, I think you have, in this case, you've got like 1250 or something. And in this problem, you have to make some quadrilateral. So maybe the quadrilateral looks something like this. That's a quadrilateral. There you go. and you want to find the quadrilateral with the smallest area. So here's one quadrilateral. Maybe you have some other quadrilateral that looks like this. I think that one probably from these points is probably the one with the smallest area that I can see. It might be this rhombus-y thing here actually, but I don't know. It's close. This one I think is more interesting. So let's move this point over to make it win. There you go. Well, actually, yeah, you can probably do better with this point instead, but whatever. So here's the interesting one. So now the question is, of all of the quadrilaterals you can pick, any quadrilateral is valid as long as it doesn't look like this. Like you can't pick self-intersecting quadrilaterals. That obviously is not valid because it's not really even a quadrilateral, to be honest. So yeah, so you want like some normal, simple quadrilateral. Might be concave or might not be convex. And now you want to see what one has the smallest area. So there you go. Here's this one. If you want to take a minute and pause, see if you can figure out how to apply this new all pairs of points idea to this problem, go ahead and do that. But otherwise you've been warned. So here's the solution. And for this problem, what we can notice is if we have some quadrilateral, like really there are concave ones and there are convex ones. So if we have some, here's a convex quadrilateral, here's like some concave one. For both of them, what we can do is we can divide them in half with some line. There's always some line that's like some diagonal that doesn't intersect the quadrilateral, even if it's concave. So it could look like this. It might also look like kind of the opposite, right? It might look like this. But in this case, you just pick the other diagonal, right? So there you go. So that's always possible to do, and you can convince yourself pretty easily just with a little bit of work on paper. But now, what you can do is if we have that line, so say we've got that line here, right? Now we might have a bunch of points on this side, and we also have a bunch of points on this side. What we're going to want to do is we know this line divides it into two halves. So really we know both halves, or both halves are independent is the important part. So we can find this point on this side, and we can find some other point on this side, looks like this one. And the answer is just going to be the sum of the areas of these two triangles. So really we just want the smallest triangle where this is the base. And we already know how to solve that problem. Like we literally just did that 20 minutes ago. So what you can do is if you have these sorted and we have these all pairs of points, we just find the first one above and the first one below. We can easily calculate the area. All right, so there are a couple caveats that I want to go over just before I end the video. And those are, especially in this problem at least, possibly in the other ones as well, if coordinates are big, like coordinates are up to like 10 to the 9, you have to make sure you use longs for everything. You can find the area of a triangle pretty easily. So if you have two vectors, their cross product will be either positive or negative area of this parallelogram. So if you want the area of this triangle, you just cross product divided by 2. And if you do that, what you have to do is you have to actually store double the area, and then at the end you can print it divided by 2, but don't divide by 2.0 as a double. Just divide by 2 as an integer, and then add a 0.5 if it was odd, because like you might not be able to store everything as a double safely, even though you might have to print it as a double. But the important part is the area is always going to be an integer or end in a 0.5. Yeah, so I guess that's that part. Also for sorting radially, you can also do that just with integers. So you could do it with like arctan 2. There are precision issues there, obviously, because you might have a bunch of vectors that are very close to the same angle, and then your array might get messed up if your like computer gets those angles just slightly wrong, or says multiple angles have the same arctangent when really they don't. So instead, if you have all of your points on a plane, if they're all on one half of the hemisphere, then you can sort by cross products. So if you take two vectors, if you take their cross product, if it's positive, then one of them should be first. If it's negative, the other one should be first. I'll leave that as an exercise to the reader or to the viewer to figure out why. But yeah, so this is possible. It's also possible to do this if they're not all in the same hemisphere, but then you just have to define some start. Usually you do it like just the positive x-axis is your start, so that's where you cut the circle in half, and then you can define everything from there. All right, so that's the all pairs of points trick. It's very helpful in my opinion. I really enjoy it. I think there are some cool problems you can do with it. And I'll leave problems on the Code Forces blog. So if you want to upsolve, get some practice with this, I recommend doing that. That's all. I'll see you on the next Code Forces round, and goodbye.